Previously, we learned that we have different types of substances. Simplest is elements. But why do we have different types of elements? What's the difference between each element and the other? What happens if you take a sample of any element and start dividing it into smaller and smaller pieces? The first acceptable model to answer these questions was Dalton's atomic theory, with the first postulate of the theory that any element is made out of tiny indivisible building blocks called atoms, which means if you divide any piece of element into smaller pieces, you will eventually reach a point or a particle that you can no longer divide into smaller pieces. This particle is called an atom. So atoms that belong to the same element are identical in the chemical nature, while atoms that belong to different elements are fundamentally different in comparison to each other. This is the same as if you have an apple and orange. Those are going to be fundamentally different with respect to each other. However, you can get smaller apples or smaller oranges. Even those that are all apples are not the same size. So similarly, yes, atoms that belong to a given element are chemically identical, but they will have different sizes, different masses, and this is what we will learn in the section talking about isotopes. The next postulate was that these atoms are neither created nor destroyed in a chemical reaction. These atoms for different elements can combine to make compounds. These combinations has to be in fixed ratios of whole numbers. So for example, if we're talking about a water molecule, this is always a combination of two hydrogen atoms combined with one oxygen atom. You cannot use fractions here because there is no fraction of an atom that can exist stably, at least. However, the assumption that an atom is indivisible was proven to be incorrect. In one of the experiments to discover subatomic particles, we put two high voltage electrodes in a vacuum tube. And when you apply high voltage, you see that there is a beam that comes out of the cathode towards the anode and can be detected on the detector right here. This beam was found to be a beam of particles with a mass of 9.11 times 10 to negative 31 kilograms. If you put a magnet perpendicular to this beam, we observe that the beam gets attracted to the magnet, which means this particle is magnetic. Also, if we put an external electric field, we observe that this beam gets attracted to the positive electrode, which means these particles are actually negatively charged. That was the discovery of the first subatomic particle, which we called an electron. Give it the symbol of an E with a negative charge indicating the negative charge of the particle. In another experiment, if you expose a sample to a beam of positively charged alpha particles, we observe that these alpha particles actually gets repelled as an indication of collision with something positively charged inside your sample, which means atoms has to contain positively charged particles inside them. Later on, we discovered that the smallest of these positively charged particles inside the atom has a mass of 1.67 times 10 to negative 37 kilograms. We called it a proton, give it the symbol P+, indicating the positive charge. So far, we discovered two subatomic particles inside the atom. The first one is a proton, which has a mass of 1.67 times 10 to negative 27 kilograms, and it has a positive charge. We also discovered a second subatomic particle that is as massive as a proton, however, it's neutral. If you look at the masses of these two subatomic particles, you can clearly see that it's almost equal. This is why we defined a new mass unit called the atomic mass unit with a magnitude that equals 1.66 times 10 to negative 27 kilograms. And based on that, you can express the mass of the proton to be 1.0073 AMU and the mass of the neutron to be 1.008 AMU. The third subatomic particle that we discovered is the negatively charged subatomic particle, which much lighter in terms of mass. It's actually 100,000 times less massive. Since any given atom is neutral, you have to have the same number of positively charged particles to negatively charged particles in any atom, or the same number of protons to the number of electrons in any given atom. Just to put the sizes and the masses of these subatomic particles into perspective, the proton and the neutron forming the nucleus are very massive. They contain 99.9% of the mass of the atom. However, they are very tiny. They exhibit very small volume. Most of the volume is occupied by the electron, which is much less massive. It's actually almost less than 0.1% of the mass. And to compare sizes to each other, the size of the nucleus, including protons and neutrons, as compared to the size of the atom itself, equivalent to the difference between the size of a ball and the size of the whole field. Most atoms are very tiny, within the range of 1 angstrom in size. This is why they are not visible by the human eye, and they're not detectable by optical microscopes. However, we were able to develop scanning tunneling microscopes, which are much more powerful. So it was possible to actually visualize single atoms. As you can see in this picture here, that was first taken in IBM labs. Atoms having the same number of protons will have the same chemical identity or the same chemical nature and form one element. The number of protons here is like the DNA of the atom, so it determines what type of element this atom belongs to. It's the same thing as the DNA that determines an apple versus an orange. And to differentiate between these elements, as we said, we give them names and we abbreviate these names to symbols. And just to include as many information as possible into these symbols, we have two superscripts and a subscript. The subscript is the number of protons of that atom, which is called the atomic number. And as we said, it determines the identity of the element. The superscript to the left is the total number of protons and neutrons together, and it's called the mass number of the atom. And it determines the actual mass of a single atom. And the superscript to the right determines the charge of that atom. And typically, if we're talking about neutral element, that charge is 0, and it's not written. So from the symbol of each element, we can learn a lot of information. The first is the number of protons, which is the atomic number of the element, written in the subscript of the symbol, as well as the total number of protons plus neutrons, which is the mass number of the element, written as the superscript to the left, and also the charge, which is usually written as a superscript to the right. So in this example right here, we have titanium with an atomic number of 22 and a mass number of 48. We can calculate the number of protons, electrons, and neutrons from this symbol. So 22 is equivalent to the number of protons, which has to equal the number of electrons because this atom is neutral. It has a 0 electric charge. The mass number 48 equals the sum of protons plus neutrons. So if you subtract 22 from 48, you will be able to get 26, which is the number of neutrons in this example. A different number of protons in a given atom will lead to different types of elements. And so far we have 118 elements. We organize them in the increasing atomic number to construct a periodic table. In the periodic table, any horizontal row is called a period, any vertical column is called a group, and the elements that belong to the same group hold a lot of chemical similarity. They're actually very similar to each other. This is why we typically give special names to different groups. So group 1 is called alkali metals, group 2 is called alkaline earth metals, group 17 here is called halogens, and group 18 is called noble gases. All the elements that belong to the same group will be very similar chemically. So that's the first piece of information that we can learn from the periodic table, is the similarity between different elements. So based on the position of the element, you will determine or predict what type of element or what type of chemical behavior you should expect. All the left-hand side of the periodic table is going to have metallic behavior. All the elements on the right-hand side of the periodic table is going to have non-metallic behavior, and those on the borderline will be metalloids. As we said, elements in the periodic table are neutral with 0 electric charge, which means they have to have the same number of protons as the number of electrons. However, electrons are able to move in and out of the atom, forming what is called ions. When an atom of a metal loses an electron, it forms a positively charged ion that is called a cation. When a non-metal element gains an electron, it forms a negatively charged ion that is called an anion. So the second benefit from the periodic table is our ability to predict what type of ion the element will form. All the elements to the left of the periodic table will tend to form cations with positive charges. All the elements to the right of the periodic table will tend to form anions with negative charges. And even the magnitude of the charge is going to form can be predicted, and it's going to equal to the group number for metals on the left hand side of the periodic table. So it's going to go +1 for group 1, +2 for group 2, +3 for group 3. A similar trend will take place in the right of the periodic table for non-metals. It's going to gain 1 negative charge for group 17, and 2 for group 16, 3 for group 15, and so on. So just to conclude what we learned in this video, we talked about the basic composition of an atom, introducing subatomic particles, protons, neutrons, and electrons, and how to calculate the number of each one of these subatomic particles in an element from the symbol of the element in the periodic table, how we used these information to construct a periodic table in the first place, and then how we learn from the periodic table similarities in the chemical behavior of the elements, and predicts the type of ion that it will form when it engages in chemical reactions.